Screen again. Are you ready, Alvin?
Yeah.
All right. Hello, everyone. We're group one. We're going to talk about graphs.
So, graphs is it's like a diagram that is used for organizational purposes and can be used to display information visually. And you could use like a table and then just convert that into a graph. So as in this graph, you can see that Anna has been partners with Dan and Flo in the past. So her vertex is connected to Dan and Flo's on the graph. And the same is true for all 9 members. If you look at it back, they're all connected if they've been partners together.
So here's some terminology about a graph. So the dots on the graph are vertexes or vertices, actually. And the lines are edges. And edges can be round or straight. And if an edge has the same starting and end point, it's a loop. And 2 vertices that are connected by an edge are adjacent. So on the right, vertices 7 and vertices 6 are adjacent to each other because they have the 6th edge in between them. And graphs can be represented with sets as well. And yeah, each edge in the edge set denoted by E of G will always correspond to 1 or 2 vertices, but you can call them endpoints. And then the correspondence between them, edges and vertices, is the edge endpoint function. And each edge that's connected to an endpoint is also incident on. It's just another way to say they're connected. And yeah, a solitary vertex is isolated. So yeah, here's our quiz part as well.
Here's the first question. So we're gonna draw a graph with and here we have 4 streets here, and they're connected to the other 3 streets via edges. And so yeah,
it's like the first example we showed. Just connect them, yeah, like this.
Yeah. So we can show you the solution for it, which is on this second to last slide.
Where is it? Here.
It's pretty simple. Like on the chart, North Street is connected to west and east, and south is connected just to east by itself. So you can see how it's organized this way. It's basically the same as the chart, but just a visual representation.
Yep. Second question is just a basic test of like in the anatomy of a graph. So here's like the answer bank, and yeah, just identify each of these objects or parts of a graph. And yeah, it's pretty
Does
simple.
anyone wanna? Okay, you wanna show them the solution?
Yeah, I'll just show them. Yeah, it's from the textbook. But yeah, that's all. That's our presentation of graphs.
Give them time to think. Okay.
Yeah, thank you.
Yeah, thanks.
Okay, and you guys can see my screen, right?
Yes, we all can.
Yeah.
Hello, class. My name is Jose Saldivia, and we're group number 2. And today we're going to talk with Mana, Soma, and myself about graph representation.
So first, I'm going to cover a little bit of terminology before we go through the examples we have. So for the terminology, first I'm going to talk about vertices. So those are represented by dots, and they do not have to be attached to an edge. And if they're not, they're considered isolated vertices. And a vertex set is basically a set containing all of the vertices in the graph. For edges, they are represented by line segments, and an edge set is basically a set containing all the edges. So looking at this diagram below, we can see that the only edge present is E1. And we know it's an edge because it's a line segment. And then we have 3 vertices. So the vertex V1 and V2 are endpoints of edge E1. And then V3 is also a vertex. It's just considered an isolated vertex because it's not connected to any edges. If you were to write a vertex set for this diagram, it would include V1, V2, V3. And if you were to write an edge set for this diagram, it would just include E1. I'll give you guys some time to write this down if you need it. Okay, so now I'm going to be talking about edge endpoint functions. So an edge endpoint function is a function connecting all of the edges to their unique endpoints. So an edge endpoint function can be written in a table format, as you can see in the bottom right. That is the edge endpoint function for the diagram on the left side. So you can see that for the first edge, the vertices at the endpoint are V1, V2. So that's what's going to be written to the right side of edge E1. Then for E2, the associated vertices are V1 and V3. So you would write those. And then lastly, for V3, it would be, sorry, E3, it would be vertices V3 and V2. So you're just writing the endpoints that are connected to the edge in the table. Okay, and then did anyone need any more time to write the notes? You can let me know. Okay, so now for this example, consider the following graph, and the question is asking you to write a vertex set and the edge set, and also give a table showing the edge endpoint function. So I'll give you guys about a minute to try to solve that.
Manap,
Yeah.
there's a comment in the chat, I think.
Oh, go back to slide 1. Yeah, I can do that. Here you go.
Oh, could you actually go to the slide right before the question,
Yeah.
please?
Yeah, I can do it.
Thank you. Okay, I'm good. You can move on, unless if someone else still needs to look at it.
Okay, I think I'll go back to the question. So this was the question. Okay, I'm going to go to the solution now. So for the vertex set, it would basically contain V1, V2, V3, V4, V5, and V6. And for the edge set, it would have E1, E2, E3, E4, E5, E6, E7. And then you can see on the bottom right, there is a table for the edge endpoint function, and it should look something similar to this, your answer. You should also take note that V4 in the graph is not included anywhere in the edge endpoint function, and that's because it's a isolated vertex, like I talked about earlier. And since there's no connecting edges, it won't be associated to any, so that's why it's not in the table. But you still include it in the vertex set because it's still considered a vertex. If anyone has any questions so far, you can let me know. I can go over anything. Okay, so now I'm going to be handing it over to Soma.
Yep. So I'm going to explain some more terms for edges and vertices. They are not difficult, but can be confusing. What's confusing is the term adjacent because it's used for edges and vertices. Let's go over the terms for edges first. The first term is loop. Loop is a loop that we saw in chapter 8 in a directed graph. If a relation R on a set A is reflexive, there has to be a loop for each element of A. That is a loop. Loop is an edge with just one endpoint, like the graph on the right. The second term is parallel. Two or more edges with the same set of endpoints are called parallel. In a graph below, H1, H2, and H3 are parallel because these edges are with the same set of endpoints.
So, excuse me, so Soma, can you explain a little bit more about the parallel part? I don't really understand that.
Okay. Okay, so H1, H2,
Yeah, oh, go ahead, say what you want to say.
H1, H2, and H3 are connected with both vertex 1 and vertex 2. So, I mean, there's nothing to say about it more than that.
I think it's basically to know if
Yeah, it's just the definition.
Yeah, if both the endpoints are like both the endpoints of the edge are the same, then it would be considered parallel. So you can see that both of them, like all three of them have endpoints vertex 1 and vertex 2. You have to have both the same, the like head and tail endpoints.
So in the basic geometry, when we consider about parallel, it's usually not connected. Why here the parallel has the different definition? It's pretty interesting. It's like we taking a different route from one point to another to the destination, right? And so these different routes can be called parallel to each other.
Let's say the vertex 1 and vertex 2.
Am I understanding correctly?
Let's say that they are different addresses. Like you're going from your...
I mean, if the endpoints are the same. Okay.
I'll go to the next slide.
Yes. The third term is incident. We say an edge is incident on its endpoints. For example, if a question is like, find all edges incident on vertex 1 in a graph on the right, the answer is H1, H2, and H3 are incident on vertex 1. The fourth term is adjacent. Two edges incident on the same endpoints are called adjacent. For example, if a question is find all edges adjacent to H1 in a graph on the right, the answer is E2, I mean, H2 and E3 are adjacent to H1.
Yes. Yes.
Yeah. Next page, please. So let's move on to the terms for vertices. The first term is adjacent. Two vertices connected by an edge are called adjacent. In the graph on the right, vertex 1 is adjacent to V2 and V3 because V1 and V2 are connected by E2. And V1 and V3 are connected by E1. The last term is adjacent to itself. A vertex that is an endpoint of a loop is called adjacent to itself.
Oh, thank you. Now I understand.
Thank you. Next page, please. Okay, so let's do some problem. Find all edges that are incident on V1 and find all vertices that are adjacent to V1 and so on and so forth. Take a few minutes and if you don't mind, type your answers in the chat. Thank you.
Can you go back to the incidence slide for a second? Okay, cool.
So you're good?
I'm good. You can go back. Mhm.
So are we supposed to speak out the answer orally or read I'll write it out?
You can type it on the chat.
Maybe like another 30 seconds.
Mm.
Okay, I think we're good to go to the solutions.
Yes, let's skip to the solutions and Well, as many of you have realized it, thank you for participating and giving us your answers. So let's go to E1, E2, and E3. They're incident on V1. Then we have V2 and V3, which are adjacent to V1. E2, E3, and E4 are adjacent to E1. E6 and E7 are going to be loops because they're going back to the same point. E2 and E3 are parallel. V5 and V6 are adjacent to themselves. And V4, that is on the center, is an isolated vertex. In the following slide, we're going to find one of the things that got my attention pretty much is that we can draw more than one graph with the same points. It doesn't matter. You can draw it in different ways. There is not a right or wrong answer. Both are correct. In the vertex sets V1, V2, V3, and V4, with the edge set E1, E2, E3, and E4, finding the endpoints, we graph A as an example. It looks kind of like a Q or like a 9 in a circle. And for B, it's exactly the same, but in a different way. This means that we can, as far as we follow the connecting points, it doesn't matter how we graph them. Now on the next slide, I'm going to let you think in a little bit. I'm going to give a minute so you can think different ways to graph the same 5 points. Which one will be the vertices? Which one will be the edges? To think about the difference. And remember, there is no right or wrong answer, but the importance is to see that both are correct ways to represent the same graph.
Wait, can you explain this question?
Yes, it's just to make you think that we have the same 5 points. Forget the connections lines. You have exactly the same 5 points, and there's different ways to represent the same graph. Like in the graph on the left, we kind of draw like
I get that. I get that. Okay.
So
I'm not really understanding what the example is trying to show.
Okay.
Are you trying to say that are you trying to say that you can create different graphs by using the same 5 points?
Yes. So you will have some vertices, they are going to be connected to other vertices by different.
Okay.
For this question, you want to make sure that, like for the graph on the left and the right, even though they look different, the edges have the same vertices. So for one line on, say on the star shape, one of the line segments is E1 and has vertices V1 and V2. Then you want to make sure that on the second graph, edge E1 still has vertices V1 and V2.
What do you mean?
So the next slide, maybe it will be more
clear. So let's maybe go to the solution.
Give me a second. Yeah, I'm just going to think about this.
So V1 in the solution, in the example of the solution, in the star shape, you have V1 connected to V2, that is the red line, and V1 connected to V5, that is the purple line or pink. So if we go to the right side,
Oh, okay. I see. So okay. So the thing is that you can change. So basically, in other words, the thing is like for V1 and V2, the thing is in order to make them the same type of graph, in other words, you have to the same vertices have to have the same edge, basically.
correct.
Okay, so in the first one, the star, V1 and V2 are together, and V5 and V1 have the same edge. So in order to make that true, what you did is that we had a point, we had a V1, V2, no, V1 be like the middle for V5 and V2, right? For the second graph.
Yeah.
Okay, cool. I just want to make that. Okay, cool.
I'm happy that you understood. Cool.
The idea is to show that when you're given like properties of a graph, like a vertex set, an edge set, and a edge endpoint function table, that you can come up with more graphs, like different looking graphs that still have all of those properties given.
Okay. Yeah.
So does anyone have any more questions?
Do we have more way of drawing this?
Possibly, yeah. I think.
So what's the general method that we apply to find the different way of drawing it?
Like how many different?
How you get the answer? Just by intuitionally change it, or you have some general method behind it?
Are you talking about how you would graph it given properties?
Yeah, with the given property.
So if I go back over here.
Endpoints, yeah.
Yeah, like Jose was saying earlier, they give all of these properties on the left side. So you use these properties they give you to build a graph. You'd kind of have to like work around. It would take a while because you need to make sure all of these are true for your graph. Like edge E1 should have endpoints V1, V3. Does that make it more clear?
Yeah, I learned a lot.
Any more questions, or are we good? Okay, so I'm gonna stop the screen share. And then we do have a quiz for you guys that you guys can take on your own time, and I'll drop the document link into the chat. And then you guys can check your answers on Canvas later. So there you go. Yep. Okay, and that's all for our presentation.
All right, I can start sharing the slides. Okay, can you guys see this?
Yes.
All right, cool. So our topic is directed graphs, connections with directions. So you're familiar with regular graphs. They have, like we just talked about it, they have vertices, and each vertice can be connected by one or multiple edges to other vertices. Consider some examples like train stations. So you might have like A might be a train station and B might be a train station. And then if there's an edge connecting those two vertices, that would represent trains traveling between those two stations. And then, hold on, I gotta go back. Okay, cool. And then another example is in the office, you have people and people either know each other or they don't know each other. So like person C in this example knows person E and B. Yeah. But then you might ask yourself, what if the train only goes one way? Or what if it's like a flight that only goes from San Francisco to New York, but not back at that time for whatever reason? Or what if you know somebody, but they don't know you, like the CEO of your company? You probably, if it's a large company, you'll probably know the CEO, but they won't know, on like at least by name, every single person who works for them. So how do we represent this? We use directed graphs. So this is like a regular graph, which is boring compared to directed graphs. What we can do is we can use arrows to signify like the direction of the connection. So in this example, person 1 knows person 3, but person 3 doesn't know person 1. Yeah. So I will hand this off to the next person.
So basically for this graph, edge and endpoint is just like the previous group says. You can see the edge is E1, E2 to E5, and the endpoint is V1 for V2 for E1. And there's an easy way to do it's why I think it's find the edge and then think about the head point, head to tail. So the head for E1 it's V1, the tail for E1 is V2. So just like that for every edge, and then you can easily find the endpoint. And next one.
As you guys probably know, many different things can be represented by graphs. Some of these things include, telephone lines, power lines, gas lines, airport flight paths, or even the internet. These systems are often very complex. So when designing such a system, a lot of questions can arise. Such as choosing what specific edges connect to what specific vertices to minimize costs or shorten travel distance, or even optimize a certain type of product or service. One type of graph that can be used to represent these connections is the hub and spoke model, which is what you see above, that connects the different cities in the US. Next slide.
Okay, and our second example is the World Wide Web, which is a system of interlinked documents or web pages contained on the internet. Users employing web browsers such as Internet Explorer, Google Chrome, and Apple Safari, etc., can move quickly from one web page to another by clicking on hyperlinks, which use versions of software called hypertext transfer protocols, which you may know as the HTTP links. So individuals and individual companies can create the pages which they transmit to servers that contain software capable of delivering them to those who request them through a web browser. Because the amount of information currently on the web is so vast, search engines such as Google, Yahoo, and Bing have algorithms for finding information very efficiently. And as you can see, the picture shown in this slide is basically showing a minute fraction of the hyperlink connection on the internet that radiate in and out from the Wikipedia main page.
So this one is the quiz. You guys can just quickly view and find the endpoint for E2. I think basically this is an easy one. You guys can put the answer in the chat. All right, so we can go to the answer key, I think. Yes, the correct answer is A. So based on the edge and the endpoint, just find the head and tail of edge 2. So the head of tail of edge 2 is V2 and V3, so the correct answer is A. And the next question. And what does the graph represent? You can write your answer in the chat. All right, so the correct answer is D, World Wide Web. So basically, this is the web that contains the data and the internet, which represent that the data and internet that it's spread out for the whole web. Yeah. And I think we are done.
There's one more thing I want to mention, which is in this example, you can specify, you could take any of these edges and you can specify a direction by, instead of writing a set of points, you can write an ordered pair of points. So like we could take the first one, E1, and we could write like a parentheses V1 comma V2 close parentheses, and that would represent an arrow going from left to right on the graph.
You can probably annotate on the screen and draw it. That'd be helpful. So at the top, you click on View Options, and then the third one is Annotate.
Oh, wonderful. Okay, yeah. So if we replace this notation with this, we can do it. Represents this basically. Yeah. And if you want to switch the direction, you could write something like this. And you would get, if I can figure out how to erase. Okay, well, you can have both at the same time. So then you would end up with something like this. Sorry, it's a little messy. But if you look closely, you can see that you have arrows going both directions. Yeah, that's just one thing I wanted to mention.
Wait, so where's group 4 and 5?
Oh, it's not us. It's 6. Is it 6 now? No. Sorry, Professor. Is it group 6 or 4? Oh, okay.
Professor?
I think she answered. She said yes. Okay.
Okay, so it's our turn.
Yeah.
And
so, okay, everyone. This is group 6. We're gonna talk about 3 definitions.
yeah, so for group 6, we all have 3 people to give the introduction about 3 different definitions. And those will be Susie and Jackie and me. So then we will have 2 questions in our quiz, which will be presented by Bishwa and Mr. Tsai. So now let's start it. Susie, we can move on.
Okay, so I will be talking about the first definition about complete graph. So better definition is let m be the positive integer, and a complete graph on n verticals is denoted by kn. So it's like a simple graph with n verticals, and exactly one edge connecting each pair of distinct verticals. If you look at the graph example 1, you can see that there's like if you look at the graph 1, you can see from every vertical, there's a line between them. So there are two conditions for a complete graph. The first one is there are no loops. So if you just look at the graph example 1, for each graph, there's no loops. And the second condition is for every two verticals, they share exactly one edge. So I also have a graph example 2, which is the non-complete graphs. And why is that? If you see the example 2, from B to D, there's no lines, or there's no way from A to D. So yeah, so think about this way. So like all the lines between each verticals, it's like a path. And no matter you go from which, sorry, and no matter you start from which point, you can always get to the another point. Yeah, so this is definition 1. Now it's Jackie for definition 2.
All right, thanks, Susie.
So we can move on to next definition, and it will presented by Jackie, right?
Right. Thanks, Tim. I'm gonna explain the complete bipartite graph, and just as the definition, this graph denoted KMN, and M is the number of V vertices. Let's just assume that vertices is in a set A, and N is the number of W vertices, and also assume that W vertices are in set B. And a complete bipartite graph must satisfy those three statements. There is an edge from each vertex Vi to each vertex Wj. There's two examples below the definition part. The first one is K3, 2, and that means there are 3 V's and 2 W's. And let me explain why there's M multiply N edges in complete bipartite graph. Because we need 2 vertex to make an edge. So we have 2 sets, which is set A and set B. If we want to make an edge between those 2 sets, we just we have M choices in set A, and we have N choices in set B. So there are M multiplies N edges. And how many vertices? That is easy to understand. We have M vertices in set A and N in set B. So we just add them together. Next, Tim is going to explain subgraphs. That's it. Tim, are you there? I think you are muted.
Oh, sorry. So my internet is extremely unstable today. Maybe I will be off. Okay, just move on to next slide and I catch up. So I'm going to talk about the concept of subgraph. So if you think about subgraph, actually don't be scared by the new definition. Just make a connection back to what we learned before in set theory. You know, the subset and the set, the original set. So the subgraph is nothing more than a subset from the original set. So it's the same thing, you know. And so when we look at the, so when we go through the formal definition, the subgraph is H is to be a subgraph of graph G if and only if every vertex in H is also a vertex in G. Every edge in H is also a edge in G, and every edge in H has the same endpoint as it has in G. Oh, it's so complex, but anyway, so it will be more easy to understand if we look at the real graph list on the example that, you know, so we categorize the elements in the graph to two groups. The first one is the vertex set, which is the V1 and V2, and then we categorize to the second subset, which is the edge set, the E1, E2, and E3. So when we try to create the subgraph, it's more like list out or drawing out all the, you know, subset from the power set, and a more detailed way of finding will be, so we firstly have V1, which is already a subset of the original graph, and then we draw the V2, and if we make a connection between V1 and V2, we have two edge. So it's E1 and E2, and then we draw a loop on V1 itself. So actually we can get 11 ways of drawing the subset out of this graph. Where I didn't post that graph on this page because of the page frame is not big enough. That's basically the concept of subgraph, and we will moving on to the quiz part. So Bishwas, please go ahead.
All right, guys. So this is the question number one for you. You can have like, I don't know, 3-4 minutes to draw this on your notebook, and then I'll expose the answer. Actually, just do a question number A, please. And it's locked. All right. I hope you have given a try. So let's go to the next slide and I'll explain the answer as well. So like Tim was saying, right, it's just pretty much a concept of subset, except it doesn't have such thing as like empty graph. So as long as you have the vertices and edge, so that can be a subset. So for example, for this question, it has 6 solutions. So the first solution is V2 by itself, because V2 is present in that main graph. The second subgraph is V1 by itself. The third subgraph is V1 and V2. And then the fourth subgraph is V1, V2 connected by the edge, the right edge, which I think is like E1. And then the fifth is the V1 to V2 connected by the left edge, which I think is E2. And then the last one is the complete graph itself is a subgraph. So pretty much it's the same concept of subset, except it doesn't have such thing as empty graph. And also to note that that you can't just have an edge and call it a subgraph. It needs the vertex as well. So I hope that is clear. If you have any questions, feel free to ask. Thank you.
So is every graph a subgraph of itself then? Like the complete thing?
Yes. So you're talking about this last one?
Yes.
Yeah. So yeah, that is a subgraph of itself. Yes.
Okay. Thank you.
I don't know if there's a terminology for that, but yeah.
Wait, can you go back to the question again? Because I'm just not like. Yeah, can you go back to the answer now? Because like the thing is, I'm not sure why you got V2 and V1 and they don't have an edge connecting them.
So you don't need to have an edge as long as you have the vertex.
Oh, this is a subgraph. Okay, I see. So so if you delete like the edges and you can arrange them in any way you wanted.
Right. But like I said earlier, that you can't just have edge by itself. It needs a vertex.
Okay. So you can't have edges by themselves, but you can have vertices by themselves. Yeah, that's right. Okay. I remember. Okay, yeah.
And if I'm wrong, please correct me, but that's my understanding.
So hi everyone. So the question 2. So as the picture is shown here, please shows that the two drawing respond to the same graph. Yeah, and I will show the question and the answer later. So as the picture here top, we can see that both the figures represent the same graph. Is anyone have any question about this one? Did anyone have question? Or we will end the presentation.
No.